Okay, so I'm very happy to announce the second speaker this afternoon, which is Peter Bruin from Leiden, who will be talking about cohomology and arithmetic duality.
Yeah, thank you. So this talk will be mostly independent of the rest of the seminar up to now, in the sense that we don't use a lot of things that are not well known. But the goal will be to understand at the end H2 with H2 étale cohomology with new R coefficients, so to understand gerbs on various things, namely abelian varieties, torsors, and also some stacks. But most of this talk will not involve stacks at all. So, unless mentioned otherwise, F will be a field. But in the applications, F will mostly be a non-Archimedean local field. But I will hopefully mention that when it is necessary. And then we can take either Galois cohomology or étale cohomology of Galois modules or étale sheaves, respectively. So when I write HI Fm, then either this is Galois cohomology and M is a Galois module, we fix some separable closure of F. Or it will mean HI of spec F étale with M, and here M is an étale sheaf on spec F. It will really make no difference, and you can just think of whichever you prefer. Okay. And something we will need a couple of times is the, so if X is a variety, F is the structure map, then we have a spectral sequence and there are again two ways of thinking about this. There's the raised spectral sequence for the sheaf cohomology of F. So you can take cohomology on F, or you can push forward and then take cohomology on F, on X, or push forward and take cohomology on F. Or well, you can also think about this as a Hochschild-Serre spectral sequence if you prefer to think about Galois cohomology. And something else that is related. You can also take two sheaves F and G, and then you can take a derived functor of Hom, so you can take X. You can write this as XQ if you want, and this gives a spectral sequence for expressing the X group. So both of these will play a role, but only in concrete cases, so only for low values of P and Q, and you get concrete long exact sequences coming from the start of the spectral sequence. Okay. Also, it's useful to say that, as usual, the H1 of a scheme with GM coefficients will be written as Picard group of X and the H2 with GM coefficients will be denoted as BR of X, the Brouwer group of X. In the paper that we are studying, often when they write BR of X, they actually mean a μr coefficients. So this caused me some confusion, but hopefully in this talk, whenever I take μr coefficients, I will write it like that and not BR of X. And so now in the case where F is a local field, from now on local field will mean non-Archimedean local field, then from local class field theory we have the invariant map which identifies the Brouwer group of F, or of spec F, with Q mod Z. And this also gives rise to a number of duality statements. So first of all, if F is still a local field and M is a finite commutative group scheme or Galois module, and the order or degree to P, where P is the residual characteristic of F. Then we can pair cohomology groups whose degrees add up to 2 for this M itself and for its dual. So we can go to the H2 with GM coefficients. So the M dual is home of M to GM. So you can take the cup product, use the pairing between M and M dual, end up in H2 with GM coefficients, and then take the invariant. Then this turns out to be a perfect pairing in the sense that it identifies each of these groups with the Q mod Z dual of the other, the Pontryagin dual. Okay, so this is something that we will need. One other thing, maybe I should go to the next board. One other thing also for these finite modules is that in this setting, still the order of M coplan to P, we have a relation between all the orders of the cohomology groups, namely the order of H0. So you can say the Euler characteristic H0 Fm, H2 Fm, divided by the order of H1 is equal to 1. So this becomes false, I believe, if the order becomes divisible by P. Okay, so these are the things we need for finite modules, finite group schemes. if this is part 1, then part 2 we start looking at abelian varieties. F should still be a local field, but we'll only need that a bit later. And I mentioned these X groups before. We're going to look at the pairing between these X group. I think it's called the Yoneda pairing, where you take exact sequence and exact sequences and concatenate them. And first of all, let me write them as XR. First group is Z, so this might look a bit silly, but then it's easier to see where the pairing comes from. Times X S A GM, so we have two extensions. And we can concatenate these into a longer extension of length R plus S. Z by Gn. But, well, the X, you can interpret them as extensions of groups, but of abelian groups, but they are also derived functors of Hom. And if you think about it in that way, then this is just the HR F with coefficients in A. And this is a HR plus S with F coefficients in Gn. Okay, and we are going to look at this for F, a non-Archimedean local field, and for small values of R and S. So for this thing which is still in X, we're going to rewrite this X using this spectral sequence, which is maybe still visible, using the spectral sequence of this maybe local to global X, sheaf X to global X. So it turns out that with the sheaf X, or if you want, the X of the abelian variety over the separable closure, if you take these things it turns out that you get 0 in almost all cases. For Q equals 0, this is just homomorphisms from A to Gm, but A is projective and connected, and Gm is affine, so these are only the affine, the constant, this is only the 0, the one homomorphism. So for Q equals 0, nothing happens. For Q equals 1, this gives exactly the dual abelian variety. So another way to define this would be to take the Picard scheme, the Picard functor, take the connected components, the identity, but that turns out to be isomorphic to
But I'm a bit
this.
surprised that you get a variety and not the K bar points of the F bar points as a gamma module.
Oh, maybe I should have. Yeah, I actually prepared this with the separable closure. So maybe you do have to do this.
Well, but the result is a
Oh, Oh, you mean that this is...
It is not a variety, your thing, right? Unless you really get...
I mean,
you get the sheaf on the small étal side of f or so given by a dual, but that's not a dual itself, I would say. You cannot take its tangent space.
Tangent space. Maybe I should just do this over. So x s of a of the separable closure.
Yeah.
Okay. Then this will just be fs points. Big zero of AFS. Is this better?
Yeah.
Okay. So this is if s equals 1, and otherwise you get 0. So that means that this spectral sequence degenerates immediately, which means that you get isomorphisms. Identifying the, let's say, the T homology, so, well, P is now T because P is the residue characteristic, of F with values in a dual, so maybe here you should think about this as being Galois homology. That's nothing but x1, xt plus 1. A with GM.
So, Peter, I mean, so when you write these x to s of A, Fs, GM, this is as extensions as group scheme, the set of extensions as group schemes over Fs.
Yeah.
Yes.
Okay. But then on the left-hand side of the board, you've got, so I can take the constant group scheme Z and I can take the x to A. But when I write it as an HR, then how, when you say this is the same as HR of F comma A, then I'm taking A as the A, K, S, Fs much as a Galois module? Or, because I don't know how to take cohomology with coefficients in a group scheme. Possibly
unless you have a big site.
Okay, so I could also do in the big étal. Does it give the same answers? Probably.
I don't
so
know if that's automatic.
Is this the complaint that I'm confusing the big and the small?
I guess
but somehow you write varieties and we expect sheaves on the small étal side or just Galois modules.
I guess I'm not like. What does HRF comma A mean? Is A like a scheme or a set, or is there a Galois module? Is it like A?
I was thinking of schemes.
It should be it should be the sheaf on the smaller tile side.
Yeah, but then it is not so clear that the x1 of A by GM gives you a dual. If you just look at the Galois modules, that's a kind of a statement.
You mean
right?
extensions of Galois of sheaves on the smaller tiles set?
But that means Galois modules. It's
Yeah,
the same thing.
no, I agree.
So
But then it's not clear
there
that
is
it's
no
fixed.
geometry.
Yeah.
Right?
Yeah.
It is probably still true. I mean, I don't know why.
Something.
Okay, so yeah, maybe I was too naive trying to just sketch. Well, so what I want to do is say where the pairing comes from, but I can also state it as a black box.
Mm-hmm.
What you get in the end. So now you take.
Because it's smooth.
You take for instance two integers R and T. R and T you take 1, 0, and 0, 1.
It's small. It's small.
You get pairings between H1 FA and H dual of F. so the cohomology, first cohomology of A with the just the f points of the dual to Q mod Z. And on the other hand, A of F times H1 F A dual so this is very symmetric if you switch A and A dual. And then the famous theorem of Tate.
And it's really it's really A V of F, not of F S. Or
The H1 for the
no,
H1?
the A V of F. It's really of F. Okay.
Because it's
Yes,
H0.
yeah, yes.
Oh, this is the H0. Oh, I'm sorry.
Yeah.
Yep.
Yeah. So we have these pairings, well, modulo the right choices in the construction for the categories we're working. Tate's theorem says that these are, again, perfect pairings. So note that the types of groups are a bit different. So these H1s are discrete torsion groups, and the A of F and A dual of F are. So I should have said here again, F is a local field, and we have taken this pairing to the H2 again with GN coefficients and taken the invariant map. So F.
But do I need the topology on A dual of F to do this? Should it be
Well,
instead of continuity?
Yeah, so I think it identifies this thing with the continuous dual of that one, and vice versa.
Okay, good. Yeah.
Topological relationships. Okay, so this is these are the main general ingredients that we need. So let's prove one of the results, which is apparently one of the key results that they will need later on. It says that if F is again a local field, still non-Archimedean, and phi is an isogeny of abelian varieties over F. Then the product of the kernels on the k points, on the f points, is equal to the product of the orders of the kernels at the k points. This product of phi and its dual. Sorry, dual goes between dual abelian varieties. The product of the kernels is the product of the co-kernels, so of BF modulo phi AF and of A dual F modulo phi B dual F.
With the kernels, you didn't finish the writing, actually.
Oh, so yes. That's because I realized I should have said what F dual was. Yeah, thank you. Okay, the proof is essentially writing down the long exact cohomology sequence of this corresponding to this isogeny and using the previous results. So we start with the sequence phi. And maybe again, think of this as the Galois modules. And we take the corresponding cohomology sequence. And this starts with the f points. AF, BF, and then there is something which, let me just continue the sequence for now. H1 with F with coefficients in the kernel of phi. Then it ends with a 0, so this is because it turns out that the H2 and higher of an abelian variety are 0. And, well, we identify these with the dual abelian varieties, so the H dual of F star, where so star is home to Q mod Z. This is now the dual map to phi dual. And that means that you get a splitting, well, maybe splitting is not the right word, you get a short exact sequence with this H1 in the middle, and on the left you get the co-kernel of phi on the f points, and on the right you get the dual of the co-kernel of phi dual. So what this gives you that's the product on the right. Is the same as the order of H1. Which by Tate's theorem is the product of the order of the H0 and H2. The same thing. And then you see that the order of H0 is just the order of the kernel of F, and the order of H2 is the order of the dual, of the kernel of the dual. Okay, so that's quite straightforward. And the corollary of this, which they need, is if phi is a self-dual isogeny, which means that the B is now the dual of A. And if you dualize phi and you identify the double dual of A with A, then it has to be equal to phi. Yeah, I hope this is clear enough. dualizing and identifying the double dual of A. Then there is only one kernel and one co-kernel. So the order of the co-kernel is the order of the kernel. Okay.
So if I can ask, your local field, can it also be of characteristic P?
I think so.
Then you want phi to be separable, I think. No?
Oh, sorry. Yes, I forgot to write this down. Yes, yeah. And the dual as well. So the degree of phi should not be divisible. Then.
Also in the mixed characteristic case. Because now you weakened the statement.
This is weaker, but I believe this theorem of Tate still needs this assumption, this to get this equality.
Oh, there, yeah.
Yeah. So.
And actually, the kernel of phi, the kernel of phi dual is the Cartier dual of the kernel of phi, right?
Yeah, that
so
too.
these two vectors on the left-hand side are equal.
Well, no, but the
the
points don't need to be the same.
Okay,
yeah. So these are not always equal. But under this assumption, this implies in particular that the kernel of phi is its own Cartier dual. But
okay, sorry.
Yeah, so we are not using Cartier duality here. Okay, let's see how much time do I have and how much there's still to do. This is good. Okay, so this is most of the sections 3.1 and 3.4 that is used later on. I will postpone one part of section 3.4 to later in the talk. Okay, for 3, this will be connected a little bit more to Bas's talk. This will be about twists of varieties. So here S, let's first do this very generally. S is any scheme, and N is an algebraic space over S. I could have taken N the scheme as well, but later on I'm not sure if the quotients that we will take are again going to be schemes in general. But in the application, everything will just be varieties. You can think of quasi-projective varieties if you want for N. Then gamma S in Bas's talk will be well, maybe slightly more generally for now. It can be a group scheme. Finite total commutative as well. Then, as we know, H1 of S with coefficients in gamma, it classifies torsors under gamma for the étale topology. we have an element of this H1, so we choose a torso representing it. The twist of n by t is defined as a certain quotient. It's nt, and we take first the fiber product of n and t by gamma. Oh, sorry, I didn't say that gamma acts on n. It can act on n in any way you want, so the quotient of n itself by gamma may not exist as a scheme. You might want to take the stack quotient, but here you've taken the product with t on which gamma acts without fixed points. So this quotient exists at least as an algebraic space. And if n was quasi-projective, then I believe this quotient should again be quasi-projective. Okay, and as Bas already mentioned at the end, in the end we will be interested in counting points on twists of spaces, of varieties, over finite fields. So that's another result of the section 3 that will be used later on. Now M is a quasi-projective variety. And the base S will now be a finite field. So we can count points on M, but we're going to count points on the quotient of M by a finite group, finite abelian group. So now really specialized to this case of an abstract group. Then the statement is that the number of points as a stack, this quotient, is the average over gamma. Like actually, the average over all the torsors. The weighting factor is the order of the group, but that is actually so we sum over all the elements of H1 k gamma, but the gamma group of k is just z hat acting trivially on gamma, so the H1 is the homomorphisms, and the number of t that we sum over is exactly the order of gamma of the number of points on all these twists. In the paper they phrase this as a corollary of a result on how the étale cohomology groups of these twists are related. But you can also do it directly.
Sorry, Peter, so
yeah.
square brackets, so the stack quotient the k value points of the set quotient is a groupoid. So then you're counting
Yes,
the
yeah,
isomorphism classes.
You haven't defined the
No,
method, so-
I was going to
I'm sorry.
define it. Yeah, sorry.
I'm
Well,
patient.
I should have defined it before starting writing out the
Don't
proof. but Otherwise,
Otherwise you get silly
otherwise you
questions.
can just add the definitions to make the proof work, which is nice. So I don't want to define this as the right-hand side. This is you take all the objects of this category. So this, just to be clear, let me put these extra parentheses. So this is a category with only finitely many objects up to isomorphism. And we have to sum them weighted by the number of automorphisms. But what are the objects? The objects are torsors, as
You're doing
Bas explained.
objects up to isomorphism? Or
Yes, sorry.
Okay.
Yes, yeah. We sum over the isomorphism classes of objects, but an object in this category is a torsor with a map to M. There exactly, we are just taking the k points, so the torsors, we get exactly these diagrams that Bas had. This map has to be the gamma torsor, and phi has to be gamma equivariant. Okay, maybe let me continue on the left. If you have a gamma equivariant map, then you also get such phi gives a map from T to. Oh, I realized that I didn't say how I wanted to take this quotient. I already erased it. This twist. So there's a choice in how you make the action, how you make gamma act on this.
N, it was N.
Yeah, it was N before, but yeah, in this, here it is M. Let me just, yeah, they changed the notation as well. I think there's no,
You're right.
it's inessential. So here, at least according to their definition, gamma acts anti-diagonally, which means that if you have an element of this product, so let me just say how it acts on points, M, T, if you act with an element of gamma, that's M gamma, T gamma inverse. So what we have to put here is, if I'm not mistaken, somebody in the opposite torsor. Maybe should, yeah. Because then, so here this acts as, so this is the same T but with the action of elements of gamma inverted. If this sends T to phi of T comma T, then this is still gamma equivariant. So then you can take the quotient on both sides and you see that you get the k point of the twisted variety. Because the quotient of this by gamma is just spec k. and by the opposite torso. And you can also see that this gives a bijection. So this accounts for, this point accounts for one, for a contribution of 1 in the term corresponding to the opposite torso, and that gives, so summing over all the isomorphism classes of torsos, you get exactly this, but we still have to divide by the number of automorphisms, which is the order of gamma, but because the automorphisms of the torso are just translations by elements of gamma. Okay, so this formula is something that will be used later on in the paper. Then, okay, I still have 15 minutes for the fourth part.
Is it useful to say that that is also the number of k points of the quotient of m by gamma in the stupid way? If I just take the variety quotient and I take the number of k points, I think that's also true.
I think so, yeah. Yeah.
And that's because if you do cohomological point counting, the coarse moduli space and the stack have the same cohomology.
Okay.
So that's nice to know,
Okay.
right?
Yeah, I didn't realize that.
Yeah.
Okay, so the fourth part comes again closer to what Bas talked about. This is about computations of a number of groups, well, computations related to a number of groups of isomorphism classes of mu R gerbs. Yeah, what do I want to say first? Maybe let me first recall something which you may have seen in other contexts. So first of all, if X is a nice enough variety, I think it's enough for it to be properly geometrically connected. Over a field F. Then we have an exact sequence of Picard groups and Brouwer groups, which we want to do some variations on. So it relates the Picard group of X to the k points of the Picard scheme of X with the Brouwer group of k. Oh, sorry, F is k. Field k. So it's in the sequence we don't see the whole Brouwer group, we see the so-called algebraic part, which I will write down in a minute. Continues with the H1. Yeah, maybe here actually we can say Galois cohomology of the Picard group of the thing over the separable closure. And then, in general, an H3 of k, although in the cases that we're interested in, this will vanish as the last thing. And this BR1 is the kernel of the full Brauer group of X. Of the map to the Brauer group over the separable closure. So the arithmetic part of the Brauer group. And first of all, we want to do the same thing, but now with mu r coefficients in the case where x is a torsor of an abelian variety. So this, I won't write it down, but if you have seen this exact sequence before, then you probably know that it comes again from a spectral sequence. And if you write down the same spectral sequence with mu r coefficients and take x torsor under an abelian variety, then you get the following result. So f is again a local field